Welcome back, everyone. Hope everyone is doing well. Right now, today we're going to revisit one of the calculus topic, which is product rules, and then how is it related to integration by parts. All right, let's get going. All right, welcome back. Today's problem is a definite integrations for this function exponential 4x cosine 3x here. All right. Now, today I'm going to present you three different methods how we can actually evaluate these indefinite integrations. First of all, we are going to start by introducing or revisit product rules, and then how is it related to integration by parts. So that's the first method. We're going to use integration by parts. Secondly, we are going to make use of the antiderivative of one particular function's relevance to this to evaluate this indefinite integration. So second method is by using antiderivative. Now the third methods, we're going to use a more unfamiliar methods, which is making use of complex number and Euler identity. All right, let's get started with this. Okay, now we're going to start by revisit the product rule. Okay, so here I'm going to let a functions of y that consists of the product of two different functions, u and v. So where the u could be functions of f, and then whereby the v could be another functions of x also, right? Okay. Now, based on the definitions of product rules, dy dx can be given by d here. All right, we're going to differentiate this with respect to x, uv, and then that would actually give us this u dv dx plus v du dx. All right. Now that is the definitions for product rule here. Okay. Now if we try to rearrange this algebraically, okay, I'm going to show you what I mean by that. Okay. Now first of all, I'm going to make use of this one here. This term is equivalence to this. Okay. Now that's how it is initially, right? Now, if we are trying to apply the antiderivative methods onto these particular equations here, so take for instance, I'm going to apply the antiderivative here. So I'm going to apply this antiderivative onto this function, first order differential equation to be precise. And then I'm going to integrate this with respect to dx. Okay, maybe I change the color a bit so that you know what we are integrating here. Okay, now that will be the same as integrating this with respect to dx also for the expression on the right hand side. So therefore we have okay, so that's how it look like. Okay, let me change it a bit so that you can see. All right, so I have already applied antiderivative for the expression on the left and for the expressions on the right here. Okay. Now, we're going to further simplify this expression algebraically. So from here we have uv is equivalence to u dv dx. I just put a bracket here so it's easier to recognize in this case. All right, so that's how it look like. And then further rearranging, we can have. All right, now take for instance, if I want to make this as the subject, for instance. All right. Now, actually, which one you want to make it as a subject? Either this one or this one. Doesn't matter in this case, right? It's all up to your liking. So take for instance, at this point, I try to make my first expression here as my subject. So therefore, it would uv subtract with this expression here. Okay, now that is the initial setup of product rules, how we transform the product rule into integration by parts. And then by integration by parts, I mean this is the formula for integration by parts. So integration by part. All right. Now, how are we going to make use of this integration by parts then? Okay. Now, we're going to compare, we're going to make a comparison between the problem on hand here. We have this. So I'm going to rewrite this. So you can see that there is actually exponential 4x cosine 3x dx. All right. Now, this is the problem that we're going to evaluate here. Okay. Now, how are we going to evaluate this? What we are going to do is just to compare this with this integration by parts that we have just derived. So from here, we can see that by comparison, we can assign u equal to exponential 4x here. So you can see that we can assign u to represent exponential 4x, whereby we can actually assign dv dx to represent cosine 3x. All right. Now that is our intentions here. All right. I hope that is clear. Now, of course, some of you are wondering, like, can we actually let u to represent the cosine 3x instead of exponential 4x? Yes, by all means we can. So here I'm going to show you that two strategies, whether it works or not, right? Okay, now by letting this u equal to exponential 4x and dv dx equal to cosine 3x, then we can start to perform the integration by parts using that formula of integration by parts here. All right, so I'm going to proceed on. Stay tuned. All right, here we are. This is our integration by parts formula. You can see that one more time. And then how are we going to make use of this formula to obtain our indefinite integrations here? So first step, we're going to let here we're going to let our u equal to e to the power 4x, and then dv dx equal to the cosine 3x. All right, so I hope that's clear. Now from here, we can differentiate this with respect to x. So therefore, we will obtain this. Okay, and then the second part, we're going to obtain the function v in term of x in this case. So in order to obtain that, we're going to integrate our cosine 3x. Okay. Now, integrating cosine 3x, we have to be very cautious because it starts with letter C, cautious, right? Okay, don't forget that. Okay. Now, that would be sine 3x over 3 here. Yep. So in this case, we drop the plus C because this is not our final um, expression yet, right? So that is 1/3 of sine 3x here. Now, once we have obtained the initial setup here, now we are ready to substitute all this setup into our integration by parts formula here. So this is our formula, right? So how are we going to make use of this? Now, since we have already assigned u to be this, therefore we can write down this as, we can write down e for x cosine 3x dx. Right, now that is the expressions that we want to, or the integral that we're going to evaluate here. Now that must be the same as, based on the formula, we have u and v. So here we have u, and then this is our v. All we need to do is just multiply them together. So I'm going to rewrite them in a more appropriate expression in this case. So I can write down as 4x sine 3x there. All right, and then following that we have subtraction, integration of v, and then du dx. So v du dx. Okay, so v we have 1/3, and then, oh, oops, we have 4/3. So I'm going to rearrange all the number um, at the outside of the integration. So therefore you have something like this, 4 over 3. That will be a v. Okay, so this is v, and then multiply with this. All right, let me check one more time if that is correct. So v multiply with du dx. So I would get 4 over 3 exponential 4x and sine 3x there. All right, now that's how it looked like in this case. All right, so that's the first part of the integration by parts there. All right, now you will notice that we do end up somewhere here. And then you're wondering, can I reapply integration by parts one more time? Yes, of course you can, right? Now we're going to try that out. So the second part, we're going to apply the integration by parts one more time, but this time this one will be our u. So we will let this to be our u, and then this part will be our dv dx, just like what we did previously. All right. Okay. Let me clear that, and then let me show you how to do that. All right. Now from here, I'm going to apply the same strategy using integration by parts for this particular section here, for this integral. All right. Okay. To do that, I will let u equal to e for x, and then here I will get du dx to be 4e 4x. Okay, and then my dv dx, will be equal to sine 3x here. All right, and then the same thing, I will obtain my v. So the v in this case should be quite obvious. It's just 1/3 of cosine 3x here. Right. So once we're done with this, we're going to substitute this into that same integration by parts formula, and then that would yield this result here. So therefore, I'm going to rewrite this. That will be 4x cosine 3x dx. Okay, that will be the same as the first part is still 1/3 there. That's what we have. All right, so maybe I'm going to write shorter a bit so that I can save more space here, right? So I have 4x over 3 sine 3x, subtract off with 4 over 3, and then this part here we're going to apply the integration by parts using this formula here, right? And then therefore I would obtain, okay, let me put a square bracket there so it's easier to identify here. So that will be uv, that will be negative 4x over 3 cosine 3x. Okay, and then subtract off with v, but because subtractions, it become plus here, so v du dx, that will be another 4 over 3 here, e for x cosine 3x dx. All right, now that's what we have, and then I'm going to rearrange this properly. Okay, so that would be, all right. Now that will be, I'm going to just rewrite it here so that we can pick up from where we are. That will be third sine 3x, and then that would yield plus 4 over 9 e 4x cosine 3x, and then 16 over 9 um, exponential 4x cosine 3x dx. All right, now that's what we have at this point of time. All right, now I hope that's clear. Okay, I'm going to continue from here. Please stay tuned. All right, here we are. I have recopied the result that we have obtained previously. Okay, from here, this is the one that we have. If you notice that the left-hand side expression exponential 4x, cosine 3x, and the other expression is exactly the same. Okay, now from here, um, I can make it easier a bit. So maybe I can let I. So take for instance, I'm going to let I to represent this integral here. Yeah, so maybe it's easier to observe in this case. That will be I equal to, so the whole integral can be represented as I. That is 4x over 3. Okay, so there you are. Right? So this integral here is similar to this, so we can represent it as I. And then from here, by manipulating this algebraically, we can combine this I together. That would actually give us 25 over 9 I. All right, there it is. And then of course, our intention is to obtain this as our I here. So what will be this integral? Therefore, this integral will be the same as, what do we have here? Let me see. That will be 3 over 25 there. So 3 over 25. And then what else? Let me see. 3 over 25 sine 3x. And then this part here would be, let me see if I got it right. Yeah, correct. Okay. So the other part will be 4e 4x over 25 cosine 3x. All right, and then there you have it. From here, I try to formally write it down what we have achieved here. What we have achieved here is we have successfully evaluated the integral of exponential for x cos 3x, and then the result of this integral is given by 3e 4x over 25 sine 3x plus 4 over 4x 25 cosine 3x, right? And then if you like, of course you can factorize that if you like. So take for instance in this case is actually exponential 4x over 25 multiplied with 3 sine 3x plus 4 cos 3x. And then there you have it. Of course, this is a indefinite integrations. Don't forget the completion of this indefinite integration. Completion start with the letter C. Yeah, and then don't forget a piece of cheesecake. Cheesecake also start with letter C. So yeah, if you like cheesecake, don't forget to put the C at the end of the indefinite integrations there. Now we have successfully evaluated this integral using integration by parts, and then um, making use of the result from the product rule. Right now, I hope that is clear. We have successfully evaluated this integral using the first methods, making use of product rules and integrations by part. Right now, stay tuned for the second methods where we are going to make use of antiderivative of one of the functions that we can trial errors, and then how we're going to make use of the antiderivative of that function to evaluate this integral. Right, stay tuned. All right, second methods. How are we going to make use of antiderivative methods to evaluate this indefinite integral? So the method is antiderivative. All right, let's look at how to work with this. Okay, now for this antiderivative methods is more challenging, um, unless you have worked with many functions in your life before, then maybe you would sort of have that library of knowledge of the variety of functions that you can make use of. So take for instance in this case, we're going to make use of one of the functions. We're going to consider this. Okay, I'm going to consider. So consider the derivative of this functions here. Okay. Now, if you try to evaluate these differentiations by using product rule, of course, then we will have, in this case, okay. So you can see that that is the first result that we have, right? And then we can label this as number one. Then, okay. Hold on first. Maybe let me rewrite that um, more clearly so that it's easier for you to see. Okay. So um, so in this case we let this as our differentiation. So just let me rewrite that again. Sine 3x So that would actually give me 4e4x. Okay, so there you have it. That is my product rule. And then the function that I'm trying to evaluate is this, which is a little bit different from the original integral here. But never mind, we will see what is the connections later on. I'm going to label this equation as equation number 1 here. All right. Okay. Oh yeah, before that, sorry. Let me clear this. I'm going to label it later on. Okay. Now from here, I'm going to take the antiderivative of this equation here. So if I take the antiderivative of this equation, I would have e4x. So if I try to apply antiderivative here, I would end up with 4e4x. All right, so that will be the antiderivative plus the other section here. All right, now that is the part where we apply antiderivative here, right? So there's nothing much we can perform at this point other than recognizing that by applying antiderivative, the result of this antiderivative do look similar, quite similar to this integral here. That is the one that we need. Okay. Let's see how we can actually proceed from here. Now for that, I'm going to label that as my first integral equations number 1. Right. Now I'm going to proceed on with the same strategy here. Okay. I'm going to consider um, these particular differentiations. This time I'm going to differentiate 3x instead, cos 3x instead. Right? And then following the same rule of product rules here, so I should end up with this. Okay, so there you have it. And then from here, applying antiderivative one more time. All right. So from here, I'm going to label this as my second equation. Right. Now, does it look familiar at this point? All right. You can see that both of these equations do have a common terms, which is exponential 4x cosine and exponential 4x sine here. All right. Now that require us to solve this simultaneously. All right. Now to do that, I can get rid of one term that I don't need. Now, since I'm evaluating this particular integral, I need to make sure that my exponential 4x cosine 3x is available at the end of this eliminations process. So I need this. Therefore, I need to get rid of my sign there. To do that, I'm going to take my number 2 multiply by a 4, and then I'm going to add up that with a 3 multiplied by my equations number 1 here. Now that's the operations that I'm going to perform now, and then this is the result that I'm going to get, right? So I'm going to time a 4 here plus with a 3. So therefore, on my left hand side, I would have 3e 4x sine 3x plus a 4 e 4x cosine 3x. Yeah, and then by doing so, I will be able to get rid of my sine term. In this case, these two terms can be eliminated, right? And then what is left is here. I'm multiplying with a 3, so therefore I will get a, in this case, let me see, a 9. So if you multiply by 3, you get a 9. If you multiply by 4 here, you get 16. So therefore, we end up with 25 exponential 4x cosine 3x. All right. And then from there, therefore, we can conclude that uh, e to the power of 4x cosine 3x dx can be written as 3e4x and then of course don't forget the completion sign. And then there you have it. How do we evaluate this integral using antiderivative methods? Now you can check with the first method, the result is exactly the same. I hope this is clear to you. Second method, we have successfully completed second method. Stay tuned. I'm going to show you the last methods, which is using um, complex number approach, and then making use of Euler identity. All right, stay tuned. All right, welcome back. We're going to look at the last methods that I'm going to present today. How we're going to make use of complex number methods, and then by making use of Euler identity to evaluate this integral. All right, now let me show it to you. Now, before we can start with this, we have to revisit the complex number through Euler identity. So, using that Euler identity, usually we have uh, complex number I, exponential complex number I theta, can be written in its trigonometry form as cosine theta plus I sine theta here. Here I need to make a remark. The I square is actually -1, just to be clear, right? Okay. Now from here, we can consider EI3. We can consider EI3x instead. All right. So whereby the 3x is our theta. So from here, we can actually write this as cosine 3x plus I sine 3x. Okay, where the I square is equal to -1. All right, this is a complex number. All right, at the same time, yeah, I can actually label this as equation number 1. At the same time, I can consider the other Euler expression, which can be written as 3x minus I sine 3x. So that will be my second equation. And then as you can guess, I'm going to sort of eliminate the sign here because I'm more interested in the cosine itself. So therefore, I'm going to add up equation 1 and equations 2. Right. So for this, I will end up with 2 cosine 3x equal to e I 3x plus e negative I 3x. All right, so you can see that. So from here, I will be able to obtain uh, an expression for cosine 3x in terms of its complex number form or Euler form in this case, which is 1 over 2 e I 3x plus e negative I 3x. Alright, now there you have it. That is my cosine 3x. Now, once I'm able to obtain cosine 3x trigonometry ratio of cosine in the Euler form, then I'm going to substitute this into my integral here. Therefore, to evaluate this integral is the same as evaluating this. Now, that is the same as all right, there you have it, right? I hope that is clear. And then from here onwards is pretty straightforward integrations of exponential, right? Now I'm going to rewrite this in the correct form so that it's easier for you to recognize its integration here. So you can see that this one can be written as 4 plus I 3 x dx. So I'm going to split it out. It's easier to recognize here. Plus half. The other one will be e 4 minus I 3 x here. Alright, so I hope that is clear. That's how it look like. And then integrating this is a piece of cheesecake at this point. Alright, it's just a simple integration of exponential here. So all we need to do is to have a half, and then the integration for the first one is basically 1 over 4 plus I3 exponential 4 plus I3 x. Right, now that's how it look like. And then the same go for the second one, which is half. In this case, it's 1 over 4 minus I3. Oops, my 3 doesn't look like a 3. So, all right, let me change that. Okay. And then from here we have e 4 minus I 3 x. All right. So basically that's how it actually look like at this point, right? And then the next part will be how are we going to finalize this in a trigonometry form? Because what we have obtained on the right hand side is combinations of complex numbers, the imaginary part and the real parts. But on the left hand side of the integral, which is this one here, they are all real. So therefore, we're going to do a bit of comparison in a while, how we can actually finalize this integral, right? So because I'm running out of space here, so stay tuned for a while. I'm going to rewrite the expression on top, right? Stay tuned. All right, here we are. This is the result that we have obtained previously. I just rewrite again. Okay. Now from here itself, as I mentioned before, what we need to do now is to isolate the imaginary component from the real component, and then we're only interested in the real component itself. So before we do that, I'm going to write it down here. Okay. So the right hand side expressions, we need to rationalize this complex expression here. So if we rationalize that, yeah, maybe I'm going to take out the half here. It's easier to work with in this case, right? So I'm going to rationalize this complex expression. If I'm going to rationalize that, I would get 4 minus I3, or 3I if you prefer here. And then that will be 25 at the top here, right? And then what I'm going to obtain for this expression is basically E4. You can see that it's actually E4x. So I try to isolate that out. Okay, I'm going to do the same thing for this. That will be 4 plus I3 over 25 also. And then that will be 4EX multiplied with negative I3X. Alright, this is how it look like at this moment. Okay, hold on, that is too long already. Okay, alright, there you have it. And then from here we can do a bit of rearrangement. So I noticed that there are lots of common factor here that we can actually take out. So take for instance, we can take out the E4x. We can bring out the 25 there. So therefore, what we end up with is this one here, I3, and then we have EI3x plus 4 plus I3 E negative I3x. Alright, there you have it. And then from here, the same thing, we're going to convert it back to its trigonometry form. So therefore, we have E4x over 50 here. That will be 4I3. Um, Same thing. So we have cos 3x. Okay, that's my first part. And then the same go for the second expression. Okay, so there you have it. So from here itself, you can do a bit of simplification and grouping the real parts from the imaginary parts here, right? So by doing so, we can have, let me see, what do we have? What do we have here? We sort of have 8. You can see that this 4 cosine 3x, and then here also have 4 cosine 3x. That would make an 8 here. And then this negative I3 multiplied with this, we know that I is, again, I'm going to write it down here just as a reminder. So I is a negative 1. So therefore, that will give me a 3 sine 3x here. And then here I also have another 3 sine 3x. So therefore, that actually make us have 8. So we have 8 cosine 3x plus 6 sine 3x. Okay, and then next, the rest are all imaginary number. So I'm going to write down the imaginary number here. I will have, um, what do we have here? Let me group this first, and then plus I. Okay, so for my imaginary counterpart, so I will have a 4 sine here. Okay, I have a 4 sine here, and then I also have another 4 sine which is negative, so they cancel off each other, right? Gone. And then the second part, I have a negative 3 I3 cos. So here I have a positive I3 cos, and then therefore, let me see what do we have. 4 cos is 4 sine is gone, and then this part here, 2 of this. Okay, so that is basically a 0. Okay, just let me check that again in case I made a mistake. All right, so here I have 4 I sine, and then I have another 3 I cos here. So I have a positive I cos here. I have 4 sine. Yes, correct. So that's what we end up at this point. So from here, yeah, we are quite lucky. So there's no imaginary parts here. And then all we need to do is make a bit of simplifications. And then we found that we have, okay, in this case, you have e for x over 25. I try to rearrange the sign so that you can compare with all our previous result that we have obtained through a different approach, right? So this one will be 4 cosine 3x, and then there you have it. It's exactly the same result as what we have obtained previously. Therefore, just to finalize this, I'm going to write that down. So this cosine, this integral is given by e for x over 25 3 sine 3x plus the 4 cos 3x. And then don't forget the completion symbol. All right. Now you can see how we are able to apply all those different branches of mathematics to solve one particular problem in this case. So bear in mind, keep your mind uh, open to all the possibility. All right. So that's the way to go, especially when we want to solve any mathematical problem there. Right. Now that brings us to the end of this presentation. I hope that it is useful to your learning. Now do take care, everyone, until I see you again. Okay. Take care, everyone. All right. See you.